We've discussed many different types of forces. For example, there's the force of you pushing on an object, where you're just maybe trying to push a block up a hill. We've talked about the normal force, where if I place a block on a table, the table will push up on the block, preventing it from falling down. That's the normal force. We've talked about the force of tension. If I hang a block from a string, from the ceiling, there's tension in the string that's pulling up on the block. We've talked about the force caused by a spring. So that if I attach a box to a spring, the spring is going to pull back with some elasticity. We've talked about the force of friction, so that if the block is sliding along the surface, or is being pushed along the surface, it's going to feel some frictional force. It could be a static or kinetic frictional force. All these forces have something in common. These are what we call contact forces. They're called contact forces because the two objects that are applying a force on each other have to be in contact. It turns out contact forces are not fundamental forces. There are only 4 types of fundamental forces. And for the most part, these contact forces are some manifestation of the electrostatic force. So contact forces are not fundamental, and the electrostatic force is fundamental. How is the electrostatic force different from a contact force? It turns out that gravity and electricity and magnetism are all examples of fundamental forces. So what distinguishes these fundamental forces from the contact forces we just talked about? Well, it turns out these fundamental forces are non-contact forces. What that means is that, let's say I take gravity as an example. You've got the Earth, you've got a baseball. The Earth is pulling the baseball back to Earth with a gravitational force. But it's not actually connected to the baseball. There's no little teeny tiny string that's pulling on the baseball. It's just that the gravitational force works over some distance. It doesn't have to actually be in contact. The same thing is true with magnets. Every kid loves playing with magnets because they're kind of weird. When you take 2 magnets, they're not even touching each other, but even without touching, they can repel each other, provided that I put like poles facing each other. So if I take the north pole of a magnet, point it towards the north pole of another magnet, I will get a magnetic force that repels the top magnet by some distance. It also repels the bottom magnet by Newton's 3rd law. Same thing is true with the electrostatic force. We have, let's say, a proton and an electron. The proton is pulling the electron towards it. That will cause it to undergo circular motion. But the 2 objects, the proton and the electron, are not in contact with each other. This is a very difficult concept for physics students to understand. How can 2 objects push or pull on each other if they're not even touching?
It's an energy field created by all living things. It surrounds us.
To deal with non-contact forces, physicists came up with the concept of a field. What is a field? Well, a field is some invisible entity that extends throughout space. And applied to forces, we're going to call these different force fields. Now, there are many different force fields that we are going to come into contact with throughout the rest of the course, no pun intended. There are many different fields we're going to come into contact with, some of which we've seen already. The gravitational field, for example, we didn't work with that too much explicitly. We didn't call it a gravitational field anyway. But it's certainly true that gravity extends throughout space, so that if I have an object over here that has some mass, and I'm near the Earth is going to pull that object toward it. And I can imagine that there's a bunch of these invisible arrows that tell me how big the force is going to be on that mass. So if I put the mass over here, it's going to get a bigger force than as I pull it away. The force is just determined by the size of that arrow. The same is true with electric charges. We have an electric field that surrounds the charge. It extends throughout all space. You can imagine that the field is made up of these arrows that get smaller and smaller as you get away from the electric charge. So if I put another electric charge here, it is going to feel a force pointing away in the same direction as that electric field, assuming we're dealing with two positive charges. We also get magnetic fields. These are fields that help you find the direction of the magnetic force. We'll deal with magnetic fields a bit later in the course. They're actually fairly easy to visualize because you can dump some iron filings on a magnet and see where the iron filings spread, and it'll give you the lines of magnetic field. So we want to deal with fields because they're going to help us understand these non-contact forces. So I have a mantra for you. This is going to be our mantra for all of the stuff that we deal with in electrostatics. The mantra is this: the charges create fields. It's the fields that then create forces on other charges. So charges create fields, the fields create forces on other charges. We are predominantly going to be interested in the electric field for the next few weeks. And we're going to define the electric field this way. The electric field is going to be a vector, and it's going to be equal to the electric force you get per unit charge. And I want to say this is some positive test charge. So we have to be somewhat careful in how we define our electric field. So the electric field is going to be different at every point in space. So let's say I have a negative charge. It turns out we can draw our electric field like this. These are known as electric field lines, by the way. We can draw our electric field like this. And every point in space that I put some positive test charge, I am going to get a different force. So if I put my positive test charge right there, I'm going to get a fairly large force because I'm pretty close to the negative charge. However, if I put my positive test charge out over here, I'm going to get a smaller force because it is further away from the negative charge, and we know that the force gets smaller as you increase the distance between the two charges. But at every point in space, I should be able to tell you what the force is. Specifically, what the force is per unit charge. Now, it turns out that for a simple situation where we're trying to figure out the electric field for a point charge, we've got a very simple formula, because we have a very simple formula for the force between 2 point charges. Which we can write just by plugging in Coulomb's law over here. This will be K Q0 over R squared. Now notice, these are different Q's. This Q is some test charge. This is the charge that I put in different spots and measure the force on it. Q naught would be this charge right here. This is the charge that's actually creating the electric field. So to emphasize that, let's just state it explicitly. This is the charge creating the electric field. Whereas this other charge is some test charge that I'm going to use to figure out what the force is going to be in different spots. The other thing I want to emphasize is that this is for point charges only. By a point charge, I just mean a charge that's a teeny tiny dot. It's a point. If I had, let's say, a whole sheet of charge, so I take the floor around me and I charge it all up, that would not give me the same electric field. If I had a cylinder of charge, that would not give me the same electric field. This only works for charges that are small enough that I can approximate them as all being in one point. So I'm going to put a big box around this, because these equations are important. We have some charge, it creates an electric field. The electric field can be determined by looking at the force you would get on some test charge in different spots throughout space. So I mentioned that when you're drawing the electric field, what you're drawing is called the electric field lines. And there are some rules for how to draw and how to interpret what the electric field lines mean. The first rule is that the electric field always comes out of a positive charge and into a negative charge. So if you have positive charges, the electric field is going to come out of the positive charges, and if you have negative charges, the electric field will go into the negative charge. You can't have an electric field coming out of a negative charge. It doesn't work that way. The drawing will give you bad results if you try to make the electric field line come out of the negative or into the positive. So we want to come out of the positive and into the negative. The next rule is that the field is stronger when the lines are closer together. We can see that just by looking at the electric field lines coming out. I can see that the electric field lines are close to each other when we're near the positive charge, but they get further away from each other as we get further and further away from the positive charge. Well, that tells me that the electric field is going to be stronger near the positive charge than further away. Further away, the lines get further apart. And we know that to be true anyway, because we know the electric field strength is going to be stronger near the charge than far away. The last rule is that the lines never cross. So why do the electric field lines never cross? Well, let's suppose for a minute that I have two positive charges. Here's positive charge number 1, here's positive charge number 2. Now, the electric field will come out of this positive charge, and it will come out of this positive charge. But if I keep continuing these lines, they would eventually cross. So what's going to happen in this case? Well, let's go back to our definition of the electric field. The definition of the electric field said that the electric field was equal to the electric force per unit charge, or per test charge. So what would happen if I were to put some positive test charge right here? Well, it would feel a force from this positive charge, pushing it that way. It would feel a force from this positive charge, pushing it that way. But the total electric force would be pushing it up this way. So if I combine the two electric fields, which is what you want to do here. So in fact, we're only going to get one very big electric field. Well, sorry, it doesn't have to be very big. You're only going to get one electric field. So what's going to happen is that my electric field lines will actually bend away from each other. And they'll go up like this. And do this on the bottom end as well. It's almost like the electric field lines themselves are repelling each other. So electric field lines never cross. It's pretty easy to see why, too. Again, this electric force is the net electric force. If my field lines cross, I would have two different electric fields there. I can't have a net electric force in two different directions, but just by definition of what it means to be a net force. It's the total. I have to add them up. So for that reason, since we're never going to have two different totals, electric field lines must never cross. The idea that electric fields never cross leads to another important concept in electricity, as well as many other areas of physics, I might add. And that's the idea of superposition. What is superposition? Superposition is the idea that if I take the electric fields from a bunch of individual charges and I add them all up, what I'll do is get some total electric field. It's just the idea. It's a fairly simple concept, although there are some subtleties with it. But it basically just says if I take multiple electric fields, to get the total electric field, all I have to do is just add up the sum of all the individual electric fields. So for example, if I have the electric field from a positive charge and a negative charge, I know the electric field comes out of the positive charge in all directions, goes into the negative charge in all directions. But if I add the sum of those two vector fields, what you get is something given by these orange lines, which essentially says that the electric field comes out of the positive and gets sucked into the negative charge. By the way, this configuration of charges has another name. It's called a dipole. But that's the idea behind superposition. The idea that there are many, if I have many charges, so if I add up all of the electric fields from all the charges in the universe, I will just get the total electric field.